Section 3.7, Rates of Change in the Sciences. For our first example, the position of a particle is given by the equation S equals f of t equals t cubed minus 6t squared plus 9t, where t is measured in seconds and s in meters. Let's find the velocity at time t. Well, velocity is going to be the derivative of our position function. So our position function is s equals f of t, which is t cubed minus 6t squared plus 9t. So we need to take the derivative of that. So we're taking ds dt. And by the power rule, that's 3t squared minus 12t plus 9. If we want the velocity after 2 seconds, we just plug in 2. So v of 2 is ds dt evaluated at t equals 2. So it's 3 times 2 squared minus 12 times 2 plus 9. So that ends up becoming negative 3 meters per second. Okay, let's get v of 4 now. So that'll be the velocity after 4 seconds. So it's the exact same thing, we just plug in 4 instead of 2. So we have 3 times 4 squared minus 12 times 4 plus 9. So that equals 9 meters per second. Okay, so when is the particle at rest? Well, the particle is at rest when it's not speeding up. So that's when the velocity is at 0. So that means that 3t squared minus 12t plus 9 is 0. But we can factor that, take out the 3. So it's 3 times t squared minus 4t plus 3, which is the same as 3 times t minus 1 times t minus 3. So we want that to be equal to 0. So that happens when t is either equal to 1 or t is equal to 3. So that means that the particle will be at rest after 1 second and after 3 seconds. To see when the particle is moving forward, we want to check when the velocity is positive. So we want v of t to be greater than 0. So that means that we want 3t squared minus 12t plus 9, which we set is equal to 3 times t minus 1 times t minus 3 to be greater than 0. So that means that either both of these terms have to be negative, because then 2 negatives cancel and become positive, because the 3 is positive, or we have to have both of these terms be positive. If one of these guys is negative and the other is positive, then we'll have a negative times positive will be a negative velocity, which we don't want. So in order to make both of these terms negative, we would have to be smaller than 1. Because in that case, we're subtracting more than we have over here, and we're subtracting more than we have over here, so both of these terms would be negative. In order to make both positive, we would have to have more than we're subtracting for both terms, so that means we'd have to be bigger than 3. So the particle is moving forward when t is less than 1, and when t is bigger than 3. Let's draw a diagram to represent the motion of the particle. Let's see, so we've got, let's say here's S, and so it starts over here when t is equal to 0. If t is equal to 0, we plug that in, we get S is also equal to 0. So the particle moves along over here. And then at t equals 1, s is equal to 4, that's when it stops moving in the positive direction and it switches directions. So far it's moving like that, then it switches, moves like that. Okay, it keeps doing that until it goes to t equals 3. And it's back at position 0. At t equals 3, it turns around again and starts moving positive again. We said that it keeps on moving positive because velocity stays positive for the entire rest of the life of this particle. So for all times greater than 3, so then it just keeps on moving positive. You have to be a little bit careful with the diagram that I drew. It's not moving up in the air. This is not two-dimensional, it's one-dimensional. It's moving back and forth along this line. I just drew it going up so that you could see the actual change in direction, because it's a little bit hard to visualize if you move back across the same line, but that's what the particle is actually doing. Let's find the total distance traveled by the particle during the first 5 seconds. Notice that if I were to just find the value of the function after 5 seconds and then subtract it from the value at 0 seconds, I would not have the total distance traveled. I would have the net distance traveled, because I would have these cancellations in between. For example, if I looked over here at t equals 0, and I took that position, and I took the position after 3 seconds, that would also be 0. If I were to just subtract those two positions, it would look like I haven't traveled any distance, but that's not true. I traveled 4, and then I traveled 4 again. I actually traveled 8. So we have to look at each of the distances separately for each time it changes direction. So let's calculate the distance from 0 to 1, because I want to include distance for when it's going backwards. So that's f of 1 minus f of 0 with an absolute value, because I want distance to be positive. So that's 4 minus 0 if I plug in 1 and 0. So that means it traveled 4 meters, as we wrote. If I look from 1 to 3, then I'm looking for the difference between f of 3 and f of 1, which is absolute value of 0 minus 4, which again is 4 meters. Okay, now I know that it's positive for the rest until 5, so don't have to worry about any more splits. So I'm looking from f of 5 to f of 3, plugging in those numbers into our function gives us 20 and 0, so it's 20 meters. So that means altogether the total distance is 4 meters plus 4 meters plus 20 meters equals 28 meters, which includes the distance it back traveled. Let's find the acceleration at time t and after 4 seconds. So acceleration is the derivative of velocity. So we can write that as d squared s dt squared, the second derivative of position. And our velocity was 3t squared, so it becomes 6t. Then minus 12t, so minus 12. And plus 9, so the derivative of that is 0. If we want acceleration after 4 seconds, we look at a of 4. So it's 6 times 4 minus 12, which is 12 meters per second, so it's per second squared. Each time we take the derivative, we go per another unit. Let's graph these guys using our handy-dandy calculator emulator. So I want to graph position, velocity, and acceleration. So position was t cubed, so I'm using x cubed, minus 6x squared plus 9x, x, and velocity was 3x squared minus 12x plus 9. And then acceleration we just got is 6x minus 12. We want to do this for t values from 0 to 5, so let's go to our window and change the minimum to 0 for x and the maximum for x to 5. Look at our graph. Ah, beautiful. Remember, the blue function is our position function. The red function, the parabola, is our velocity, and the black function is our acceleration. So let's grab that, and we'll put away our calculator. Okay, when is the particle speeding up? When is it slowing down? So it's speeding up when either the velocity is positive and increasing or negative and decreasing. So that means that the velocity and the acceleration are both positive or both negative. So we need to look for when velocity and acceleration have the same sign. So looking at our graph, we see that velocity is positive over here, but acceleration is negative over there, so that's not going to work. However, velocity becomes negative over here, and acceleration is also negative over there. So that works. In fact, velocity is still negative, acceleration is still negative, so it looks like between 1 and 2, the particle is speeding up. If I look back at my graph, I want to find another spot where they both have the same sign. It looks like it's not over here, because over here acceleration is positive, but velocity still hasn't gone above the y-axis, the x-axis, so it's still negative. But over here, velocity is positive, acceleration is also positive, so it looks like any time after 3, the particle is speeding up. It makes sense too when you look at the graph. You could see it's like kind of slowing down, and then it starts speeding up downward, but then it slows again, and then it speeds up again forevermore. So our particle is, it speeds up when t is between 1 and 2, and also when t is bigger than 3. It slows down when velocity and acceleration have opposite signs, so it slows down for the other values. If you look at 0, you can see velocity is positive, acceleration is negative, so it's slowing down at 0. However, it gets up until 1, and at 1 the velocity is 0 altogether. When the velocity is 0, the particle is at rest. So it's not slowing down at 1, it's at rest at 1, so we won't include that. Similarly, at 2, it's at rest again. And because acceleration is 0. Well, sorry, at 2 it's not speeding up or slowing down. And at 3 it's not speeding up or slowing down. So that means that this thing slows down when t is between 0 and 1, including 0 but not 1, and when t is between 2 and 3, because that's when the acceleration and velocity have opposite signs. For our next example, if a rod or piece of wire is homogeneous, then its linear density is uniform and is defined as the mass per unit length, where rho equals mass over length. It is measured in kilograms per meter. Suppose, however, that the rod is not homogeneous, but that this mass is measured from its left end to a point x is m equals f of x, as shown in the figure. So we're looking at part of the rod having more mass than another part of the rod. In this case, the average density is the average rate of change over a given interval. Okay, average rate of change, that's the slope of the secant line. The linear density is the limit of these average densities. So that means the linear density is the limit of the slope of the secant line. So the linear density is just the derivative. If m equals f of x equals square root of x, where x is measured in meters and m in kilograms, let's find the average density of the part of the rod given by x between 1 and 1.2 and the density at x equals 1. Okay, so average density is change in mass over change in x. So that'll be f evaluated at 1.2 minus f of 1 over 1.2 minus 1. So that's square root of 1.2, because f is square root of x, minus square root of 1 is 1, over 0.2, which is approximately 0.48 kilograms per meter. We now want, so that's the average density. We now want the actual density, the density which is measured by the limit of the average density. So that's rho equals dm dx, our derivative, and we want it at x equals 1. So remember, the derivative of square root of x is 1 over 2 rad x. You write it as x to the half, and then you move the exponent over using the power rule. We're going to evaluate that at x equals 1. So that equals 0.50 kilograms per meter. Both the average rate of change and the average density and the density are in the same units because they both represent rates of change. However, one's the average rate of change and one is the instantaneous rate of change. The average current during a time interval is the average rate of change of the net charge over that interval, and the current at a given time is the limit of the average current, which is the rate at which charge flows through a surface measured in units of charge per unit time. The quantity of charge Q in coulombs, C, that is passed through a point in a wire up to time t, measured in seconds, is given by this polynomial Q of t. The unit of current is an ampere, where 1 ampere is 1 coulomb per second. So let's find the current at 0.5 seconds. So we'll use I of t to be our current function. It said, let's see where it said that. Average current is the average rate of change, and the current is the limit of the average current. So that means that the current is the derivative, because it's the limit of the average rate of change. Okay, so we take the derivative and we get 3t squared minus 4t plus 6 using the power rule. So now we want it after 0.5 seconds, so that's I of 0.5. So that's 3 times 0.5 squared minus 4 times 0.5 plus 6. So that's 4.75 coulombs per second, which we have the special notation amperes for. Okay, let's do the same thing for the current after 1 second. So it's 3 times 1 squared minus 4 times 1 plus 6. So that's 5 amperes. Okay, at what point is the current the lowest? Well, notice that the velocity is this guy right over here. If we were to graph that, it looks like a parabola. So we want to know when the velocity will be at its lowest. That's over here. So the velocity is at its lowest over here when the tangent to velocity has a slope of 0. So we want to know when the derivative of velocity is 0. So we want to look sorry, not velocity, I keep saying velocity, but in this case it's actually current. I want to know when the derivative of current is 0. So we want the second derivative of charge. So we want Q double prime. I want to know when that is 0. So if we take the derivative of I of t, the current, we get 6t minus 4 is equal to 0. So that means that 6t equals 4. So t is equal to 2/3, which is roughly 0.67 seconds. The concentration of a reactant A is the number of moles, where 1 mole is 6.022 times 10 to the 23rd molecules per liter, and is denoted by A, with brackets, for a chemical reaction where A plus B goes to C. So these guys are reactants, and C is the product. The average rate of reaction during a time interval is the average rate of change of the concentration of the product over that interval, and the rate of reaction at a given time is the limit of the average rate of reaction. So our average rate of reaction is the slope of the secant line, that's our average rate of change, and the rate of reaction is the limit, so the rate of reaction is the derivative. Okay, if 1 molecule of a product C is formed from 1 molecule of reactant A and 1 molecule of reactant B, then the initial concentrations of A and B have a common value, so both of the concentrations are equal to A, then the concentration of the product is given by this function, where K is just some constant. So let's find the rate of reaction at time t. So we said that the rate of reaction is the limit, so the rate of reaction is the derivative. So we want to look for dc dt, derivative of concentration with respect to time, and that's concentration of product. So that's we have to use the quotient rule. So we get AKT plus 1, that's just the denominator, and then we take the derivative of the numerator, we get A squared K, and then we subtract the numerator, A squared KT, times the derivative of the denominator, which is just AK. And all of that gets divided by the denominator squared. So AKT plus 1 squared. Okay, so then we multiply through everything. Simplifying up, we get A cubed K squared T plus A squared K minus A cubed K squared T all over AKT plus 1 squared. So notice A cubed K squared T minus A cubed K squared T cancels. So all we have left with is A squared K over AKT plus 1 squared. So kind of similar to what we started with, but not exactly. Okay, so let's show that if X is the concentration of C, then dx dt is this thing. So we already calculated dx dt is this, because X is C. So we just have to calculate this and make sure that this matches with that. So let's do that. We have K times A minus X squared. So that's K times A minus, so we have to look back. This is what X is, because X is the concentration of C. So we plug that in. So we get minus A squared KT over AKT plus 1. And we square that. So then that equals K times, we're going to find a common denominator now, A times akt plus 1 minus a squared kt all over akt plus 1. Okay, so that's kind of cool. We have a times akt, so this is a squared kt, and then this is a squared kt, so those will subtract and cancel. So we just have the a times 1, so all we have left with is k times a over akt plus 1. So that means that when we square everything, we get a squared k in the numerator, and in the denominator we get akt plus 1 squared. Oh, cool, so it does match. Not bad. So that is equal to dx dt. Okay, let's see what happens to the concentration as the time goes to infinity. So we want to know the limit as t goes to infinity of the concentration. So that's the limit of a squared kt over akt plus 1. So in order to evaluate this limit, we want to try to get rid of the t in the denominator so that we can see what so we can see a limit that we can actually evaluate at infinity. So we'll divide the numerator and denominator by t. So we get a squared k over t over akt plus 1 over t. So then that becomes the limit as t goes to infinity of, sorry, there's supposed to be a t over there. I was like wondering how that's going to cancel. So that becomes the limit of a squared k over akt over t cancel. So we just have ak plus 1 over t. Okay, so now we only have t in the denominator of the denominator. So that means that this thing will go to 0 as t goes to infinity. As t gets really, really big, it gets really, really small. So we just have a squared k over ak. So all we have left with is a squared k over ak, so it's just a. So that means that as t goes to infinity, the concentration, the C of the products, becomes equal to A, which is the concentration of the reactants. They were both equal to A. Okay, what happens to the rate of reaction as T goes to infinity? So we want to take, instead of just the limit of concentration, now we want the limit of the rate of reaction, which was the derivative. So that's the limit of a squared k over akt plus 1 squared. So we keep our a squared k, and then we want to expand the denominator. So we get a squared k squared t squared plus 2ak t plus 1. Okay, so let's do the same trick we did last time. We want to get rid of that t squared in the denominator. So we'll divide the numerator and denominator. So this is the limit of a squared k over t squared over a squared k squared t squared plus 2akt plus 1 also over t squared. Okay, so we divide through. It looks like we have to keep our a squared k over t squared in our numerator because there's no t to cancel. In our denominator, the t squared and t squared in the first term will cancel. So we just have a squared k squared. Then we have 2ak over t because one of the t's cancels. And we have 1 over t squared. Okay, so this is nice. Now t is only in the denominator of the, of each of these fractions. So that means that in every single case where t is in the denominator, as t goes to infinity, those fractions go to 0. So we have 0 over a squared k squared plus 0 plus 0. 0 divided by a non-zero number is equal to 0. So that means that as t goes to infinity, the rate of reaction dc dt goes to 0. So what do the results of parts C and D mean in practical terms? Well, in practical terms, C tells us that if the reaction keeps going, basically indefinitely, then it eventually reaches equilibrium, because that's when the concentration of the products equals the concentration of the reactants. They just equal out. And then D tells us that the rate of reaction at equilibrium, as you just keep going, well, it just stops completely, so it's 0. Which makes sense. Eventually, if you leave the reaction going on long enough and you reach equilibrium, then the reaction just stops. Example 5. If a given substance is kept at a constant temperature, then the rate of change of its volume V with respect to its pressure P is the derivative dV/dP. The compressibility is defined by this isothermal compressibility beta minus 1 over V dV/dP. The volume in cubic meters of a sample of air at 25 degrees Celsius was found to be related to the pressure P in kilopascals by the equation V equals 5.3 over P. Let's determine the compressibility when P is 50 kilopascals. So we want beta at P equals 50, so that means first we have to calculate what dV/dP is at P equals 50. So if V is 5.3 over P, that's the same as 5.3 times P to the minus 1. So we move that minus in front. We get 5.3 over P squared because we reduce the power of P by 1. Okay, so that's plugging in 50. We get minus 5.3 over 2500, which is equal to minus 0.00212 cubic meters per kilopascal. Then we want beta, our compressibility. So that's minus 1 over the volume times dV/dP at 50. So we're doing all this at 50. So we plug in what we just got, the 0.00212. The negative cancels with the negative in front of the 1 over V. So we just have dividing by 5.3 over 50. So that equals 0.02 cubic meters per kilopascal. But then we took a derivative, so it's per cubic meter. Let n equal f of t be the number of individuals in an animal or plant population at time t. The average rate of growth during a time period is the average rate of change of the growth of the population over that time period, and the rate of growth at a given time is the limit of the average rate of change. So the rate of growth is the derivative. Let's suppose that a population of bacteria doubles every hour. The population function representing the bacteria's growth can be found to be n equals n naught times 2 to the t, where n naught is the initial population and the time t is measured in hours. Let's find the rate of growth for a colony of bacteria with an initial population n naught of 100 after 4 hours. So we're going to look for dn dt, and that's the derivative of n naught times 2 to the t. So remember, for exponential functions, it's just the function itself times the natural log of the base. Okay, if n naught is 100, then we can plug in 100, and we can evaluate dn dt at 4. So we plug in 100, we plug in 4 for t, and we get that it's 1600 times ln 2. So it's roughly 1109 bacteria per hour. The shape of a blood vessel can be modeled by a cylindrical tube with radius big R and length L as illustrated in the figure. The relationship between the velocity v of the blood and the distance r from the axis is given by the law of laminar flow, where v equals p over 4 times eta times L times r squared minus r squared, where eta is the viscosity of the blood and p is the pressure difference between the ends of the tube. If p and L are constant, then v is a function of r with domain from 0 to r. The velocity gradient at a given time is the limit of the average rate of change of velocity. So velocity gradient is the derivative. For one of the smaller human arteries, we can take eta to be equal to that, r equal that, L equal that, p equal that. Let's find the speed at which blood is flowing at r equal that and find the velocity gradient at that point. So let's first find the derivative dv dr. Okay, so that's p over 4 times eta times L times 0 minus 2r. Because with respect to r, big R is a constant, and so is everything else. So little r is the only variable here. Okay, so that we have minus p times r over 2 eta L. Let me simplify. Okay, now let's try plugging in all these numbers they gave us. We know that eta is 0.027, big R is 0.008, L is 2, and P is 4,000. Those are all of our constants. So that means that our original function, V, is equal to 4,000 over 4 times 0.027 times 2 times 0.00064 minus r squared. So that's about 1.85 times 10 to the 4th. Notice we're using scientific notation now because our numbers are so big or so small, times 6.4 times 10 to the minus 5th minus r squared. Okay, we wanted to find speed at which it's flowing at 0.002. So we're looking for this velocity at 0.002. Okay, so that's going to be roughly 1.85 times 10 to the fourth times 64 times 10 to the minus 6. We just adjust this a little bit so that it'll match up with what we get when we plug in r, because that becomes 4 times 10 to the minus 6. So when we multiply everything through, we get 1.11 centimeters per second. So that's the speed at which the blood is flowing at r equals 0.02. Let's look now for the velocity gradient at that point. So the velocity gradient is dv dr. We're doing that at r equals 0.002. So that equals minus 4,000 times 0.002, plugging in all of our constants, over 2 times 0.00, no, too many O's, got carried away, 0.027 times 2, which is about negative 74 centimeters per second, but then per centimeter. So what that means is that this is the rate of change of velocity. So the velocity is decreasing as you go away from the center. So if you look as you travel from the center of the blood vessel, the velocity decreases. Suppose C of x is the total cost that a company incurs in producing x units of a certain commodity. The function C is called a cost function. The instantaneous rate of change of cost with respect to the number of items produced, called the marginal cost, is the limit of the average rate of change of the cost. Suppose a company has estimated that the cost in dollars of producing x items is 10,000 plus 5x plus 0.01x squared. Let's find the marginal cost at the production level of 500 items, and let's compare it to the actual cost of producing the 501st item. Okay, so our marginal cost, we said, is the limit of the average rate of change, so the marginal cost is the derivative C prime of x. So by the power rule, that's 5 plus 0.02x. So let's look for C prime of 500. So that's 5 plus 0.02 times 500, which is about $15 per item. So that's how much it costs to produce items at around after producing 500 of them. So we would expect that the 501st item probably cost about $15 to produce. Let's see how much it actually costs. We look at how much it costs to produce 501 items minus how much it costs to produce 500, and that difference gives us the actual cost of producing that last item over 500. So that's 10,000 plus 5 times 501 plus 0.01 times 501 squared minus 10,000 plus 5 times 500 plus 0.01 times 500 squared, which is equal to $15.01. Alright, so that's pretty good for our marginal cost function. It looks like C prime of 500 actually does approximate the actual cost C of 501 minus C of 500 pretty well.